This is the 12th lecture on metric spaces. So in this lecture we will be doing uniform continuity. So we'll begin with the definition and some motivation for this type of continuity. Let us consider two metric spaces x dx and y dy. Y dy. Let us consider a function f which is continuous at each point. So we have a function x to y which is continuous, i.e. f is continuous at each point x naught in x. In the definition of continuity, when x naught and epsilon are specified, we make a definite choice of delta, so that dy of this y distance between fx and fx naught is less than epsilon whenever x distance between x naught and x is less than delta. This describes that delta as this describes delta as dependent upon x naught and epsilon. So we may write delta to be equal to delta x naught and epsilon to specify that, to emphasize that x naught and delta depends on x naught and the choice of epsilon. If delta x naught epsilon can be chosen in such a way that its values have a positive lower bound when epsilon is kept fixed and x naught is allowed to vary over x, and if this happens for each epsilon, then we have the notion of uniform continuity. More precisely, we have the following definition. Let x dx and y dy be two metric spaces. A function f from x to y is said to be uniformly continuous, is said to be uniformly continuous on x if for each epsilon positive, if for each epsilon positive their x are delta positive. Now this delta positive depends on epsilon alone, depending on epsilon alone, such that y distance between f of x1 f of x2 is less than epsilon whenever x distance between x1 and x2 is less than delta. So this delta doesn't depend on the choice of the domain, the inputs of f. So this is true for all x1 x2 in x. So in this case f is said to be uniformly continuous on x. every function f from x to y which is uniformly continuous on x is necessarily continuous on x. However, the converse may not be true. We'll do a couple of examples to verify this thing, that a continuous function need not be uniformly continuous. So let us take this example 1. Let x dx be equal to y dy is same as r d, where x and y they are both equal to the set of real numbers, and dx and dy is the metric dy. D is the usual or standard metric on x, where d is the standard metric on x, on r I mean. Define f of x to be equal to x squared, where this x belongs to r. So we will show that this function is not uniformly continuous. Note that f(x) being a polynomial, it is continuous over the real line r. In order to show that it is not uniformly continuous, we have to exhibit an epsilon for which no delta works. Indeed, f is continuous on R. To show f is not uniformly continuous, we have to exhibit an epsilon positive for which no delta works. Let us take epsilon to be equal to 1 and delta positive be arbitrary. Now choose x1 to be equal to delta by 2 plus 1 by delta, and x2 to be equal to 1 over delta. Then d of x1 x2 which is equal to absolute value of x1 minus x2, and that is equal to delta by 2 plus 1 over delta minus 1 over delta, and that is delta by 2, which is less than delta, because delta is a positive real number. We do not need to take its absolute value. But absolute value of but d of f of x1 f of x2 is the same as absolute value of f of x1 minus f of x2. So this is equal to delta over 2 plus 1 over delta square minus 1 over delta square, that is called delta square over 2 plus, so this is not square here, this is just delta, plus twice delta 2 by 2, delta by delta, twice delta by 2 into 1 over delta, and that is 1 minus 1 over delta square, plus 1 over delta square and minus 1 over delta square. So this is equal to, so this delta square over 2 square, this is this and this goes, so this will be equal to 1 plus delta square over 4, which is strictly bigger than 1. Thus whatever delta positive may be, their axis points x1 and x2 such that thus whatever delta positive may be, there exists points x1 and x2 such that this is called epsilon, such that x1 minus x2 is less than delta, but f of x1 minus f of x2 is bigger than epsilon, which is equal to 1. So we conclude that this f is not uniformly continuous. Let us do another example. Let us take the function f from the open interval 0 1 to the set R of real numbers defined by f of x is equal to 1 over x. We claim that this function is not uniformly continuous. Then f is not uniformly continuous. To prove this, we have to exhibit again an epsilon positive for which no delta works. To prove this, we need to exhibit an epsilon positive for which no delta positive works. Let us take epsilon to be equal to 1 over 2 and delta be any positive real number and delta positive be any number. Let us choose x1 to be equal to 1 over n and y equal to 1 over n plus 1. Let us draw a figure over here. So this is the graph. So this is f of x is equal to 1 over x. Now this is point 1 over n. This is over this is x1 over here, and let us take this x2, which is 1 over n plus 1. So this is f of 1 over n. So this is f of 1 over n plus 1, which is equal to n plus 1, and this is f of 1 over n, which is equal to n. So this distance over here, this is equal to 1. N plus 1 minus 1, that is 1. And y is equal to n plus 1, where n is a positive integer. But n is a positive integer such that n is bigger than 1 over delta. Delta is any positive real number, and we have chosen n such that n is bigger than 1 over delta. Now x1 minus x2, that is called 1 over n minus 1 over n plus 1, which is equal to 1 over n into n plus 1, and this number is indeed less than 1 over n. Now if n is bigger than 1 over delta, 1 over n is less than delta, so this is less than delta. But f of x1 minus f of x2, this is equal to n minus n plus 1, which is equal to 1, and this 1 is bigger than epsilon because we have chosen epsilon to be equal to 1 over 2. So we have exhibit an epsilon for which no delta works. So this implies that this our function is not uniformly continuous, i.e. thus whatever delta positive may be, there exists x1 and x2 such that absolute value of x1 minus x2 is less than delta. And this doesn't imply f of x1 minus f of x2 is less than epsilon, which is in our case equal to 1 by 2. So f is not uniformly continuous. Now let us do one example of a uniformly continuous function. Let us take a function f from the closed interval, unit interval 0 1 to the set R of real numbers, defined by f of x is equal to x square. Now we have to prove this is uniformly continuous. Let x1 and x2 belong to the unit interval 0 1. Then absolute value of f of x1 minus f of x2, this is equal to x1 square minus x2 square, this is equal to x1 minus x2 times x1 plus x2. This is less or equal to, this is further equal to absolute value of x1 minus x2 plus and absolute value of x1 plus x2. Now by triangle inequality, this is less or equal to absolute value of x1 plus absolute value of x2 times absolute value of x1 minus x2. Now x1 and x2 are the real numbers in the closed interval 0 1, so this is further less or equal to, so this can be at most equal to 1, and same is the case here, this can be equal to at most equal to 1, so this is less or equal to 2 times absolute value of x1 minus x2. Now if we choose now for epsilon positive, choose delta to be equal to epsilon over 2, then absolute of x1 minus y1 is less than delta, i.e. epsilon by 2. This implies mod of f of x minus f of x not y, this is x1 x2, this is x1 minus f of x2, this is less or equal to 2 times mod of x1 minus x2, this is less than 2 delta, which is further equal to epsilon, since delta is equal to epsilon by 2. This proves that epsilon is uniformly continuous. This proves that epsilon is uniformly continuous. Thank you so much.